Well, welcome to Twitter. I'm Robbie Dannett, and I lead the data science and user insights group for the Vine team. Data and statistical analysis are obviously a very important part of what we do, and we're very excited to be hosting this event. As Twitter and Vine have grown, I've been amazed at the quantity of data that our services have generated. And one of our greatest challenges is learning how to understand and make use of all this information. It's obviously a very exciting time to be in this field, and we're constantly looking to expand our team. Feel free to approach me afterwards if anyone has any questions. Welcome again.
Okay, just a few quick announcements. I know we all want to get to Hadley as quickly as possible. First up, as always, any jobs? Is anyone hiring? I know Twitter's hiring. Vine's hiring, Twitter's hiring. Besides Vine and Twitter, anyone normal job postings? Vinny is not here, so he's usually our guy. Neither is Sar. Okay, so no one's hiring. That's a sad state of the economy. Yes. The pizza today came from Williamsburg Pizza in the Lower East Side. They have multiple locations, so if everyone wants to go to bit.ly/pizza poll and vote on it, excellent, good, average, poor, never again. So everyone, you have smartphones, bit.ly/pizza poll. I don't see anyone doing it. Thank you. Any other good examples? Thank you. Everyone follow the lead. We need more votes. All right, awesome. There's also Strata's coming up at the end of the month, I believe, or beginning of next month. Who's speaking at Strata? Are you speaking at Strata? Who else is speaking? Anyone here speaking at Strata? Seriously, no one? Usually someone in this group speaks. All right. Anyway, if you guys want discounted, this is really loud. If you guys want discounted tickets, you can go to the website and use code UGNYHACKR20. All right, that's the 20% discount code for members of this group. Saves you 20%. It's an expensive ticket, so 20% will help out a lot. UGNYHACKR20. October 7th, everyone knows I'm obsessed with pizza, right? Yep. We have an amazing event called Slice Out Hunger. It's where we have pizzerias from all over the city, like Di Fara's, Lombardi's, Keste, donate pies. We sell them all for $1 a slice. Then we have matching donations, and every dollar we raise feeds 5 people at the food bank for the city of New York. Last year, we raised enough money for 100,000 meals. So if you Google Slice Out Hunger as part of Scott's Pizza Tours, come to that event. It's an awesome event. You get to have awesome pizza, and you get to help feed homeless people. So it's a really good cause. Complete opposite of that, after this talk, we're going to the bar. We're probably going to go to Flight 151 over on 8th Avenue and 17th Street. It's a bit of a dive bar, but I figure that'd be cool for this crowd. We'll figure out exactly where we're going to go, but let's assume Flight 151. As soon as we're done talking, we'll all make our way to the bar and have some good cheap beer. Thank you to Twitter, by the way, for hosting us and giving us their free beer. Thank you to Gene Exter for filming this, and we'll eventually post it online. And we're live streaming this on Periscope. I figured we're at Twitter, we might as well try their technology. Hopefully my camera will work this whole time. How many people are already on it? I don't want to know. A lot are already on it. Awesome. All right, cool. And lastly, we've been selling these things for a while. We have a few different designs. Right. Can we see the other one? Can we see one of the black ones? So this is IR New York. This was designed by Adam Hogan, a former member of our group. He's unfortunately moved to Chicago. Then this was designed by Drew Conway. Everyone knows Drew Conway. Right? NYC Data Mafia. And up here it says R. Right? You want to buy them? $20 a piece. Come see Vivian or Dan. We have a whole bunch, mostly larges. We have a couple extra larges and mediums. And if you need a different size in the next batch, we can get it to you. Thank you. And the first recipient of the IR New York t-shirt will be Hadley Wickham. So...
Wait, I have an announcement that wasn't a job.
Any announcement, yeah, come on.
Okay. I've been working on a package for doing things like taking a sample of 1,000 random lines from a really, really huge file, or like lots of really, really huge files, And I just did it because it was like fun to do the survey math and do it. But as far as I can tell, it's totally useless. So if you have like really huge files that you would like to take random samples of, talk to me because then I'll like maybe write something that will be useful to you.
That's coming from Thomas Levine, who made me a letterpress CSV file. Yeah. Go to his website. He has all sorts of really cool stuff. He really does. So, with that, anyone else like call out and embarrass? All right, cool. With all that, everyone knows Hadley Wickham. I'm not going to bother introducing him. Round of applause and enjoy his talk.
Thanks, Jared. So today I'm going to talk about pipes. And in particular, I'm going to talk not just how to use pipes, but how to create packages, how to create software ecosystems that work really well with a pipe. So I'm going to tell you about pure, predictable, and pipeable functions and why I think they're cool and important. So how many of you have seen this guy before? The Magritte pipe operator. Awesome. How many of you love the pipe? Okay, awesome. How many of you hate the pipe? Okay, that's pretty good. I gave a talk a couple of months ago, and in the audience were the two people in the world who hate pipes the most. So there's only two people here. You didn't seem to hate pipes that much. So this guy, the pipe, comes from the Magritte package by Stefan Bruck. And I'm going to, a lot of my packages take advantage of this pipe. And I'm going to kind of talk about why I think it's cool and important and useful, and how you can write your own code to take advantage of it too. Now, if you haven't seen the pipe before, I'm going to illustrate it with a little story about a little bunny called Fufu. Now, Fufu hopped through the forest, scooped up a field mouse, and bopped it on the head. Now, if you write that sequence of operations and kind of like the functions, using function composition, you get something that's a little bit hard to read, because you're going to read it from the inside out, or from right to left, which is a little hard if you're an English speaker. And the other problem is the arguments to each function can end up spread quite far apart. So what the pipe allows you to do is rewrite it like this. This code does exactly the same thing. It's interpreted exactly the same way by R, but is now much, much easier to read. So Fufu hops through the forest, then scoops up the field mouse, then bops on the head. And I think then is a really natural way to pronounce this operator, particularly when you're dealing with these sort of sequences of verbs. So the pipe doesn't change the computation at all. In terms of R, R interprets it basically exactly the same way as this. But for the human looking at this code, I think this bottom one is much, much easier to read. And I think that's important because code is a vehicle of communication. It's obviously a vehicle of communication between you and the computer, but it's also really important because it's a means of communication between you and other people. And every project you work on always has at least one other collaborator, and that collaborator is future you. And if you're anything like me, future you actually knows a lot of different things than current you, and remembers different things. And whenever present you takes a little bit of time to make sure your code is easy to understand, future you is really going to be grateful. So just a little bit more detail, this is what the pipe does. It takes the thing on the left-hand side and basically inserts it as the first argument on the right-hand side. So do x, then f of y becomes f of x and y. And of course we can chain that together typically to create more complicated sequences. So it turns function composition, and I'm going to talk about why I think functions are so important and so useful very shortly. It takes functions which are programmatically really awesome and turns them into this sort of sequence of imperative operations, which is really, really easy for humans to understand. Now here's a little example of a more complex workflow with pipes. This is one from Zeb Ross, who analyzed some Shakespeare data. So even if you don't know any of these packages at all, even if you don't know these functions, even if you only have the rudiments of R, you should still be able to kind of follow this code and get a sense for what's going on. So we're going to create a variable called word count. So you're probably going to guess we're going to be counting some words. We're going to start off with the Shakespeare data set. We're going to group it by word. We're going to summarize it, counting the number of occurrences and the total number of words, and then we're going to arrange it in descending order. Then we're going to create this thing called top 8. We take this Shakespeare data again, and we do a semi-join. How many of you know what a semi-join is? Okay, if you don't remember anything else from this talk, I'd highly encourage you to go out and find what a semi-join is. Because semi-joins are really, really useful tools. So most joins, I think of them as mutating joins. They're joins that add extra columns to your data frame. Semi-joins, on the other hand, are filtering joins. They don't affect your columns, but they do affect the rows you have. So a semi-join here is going to just keep all of the rows of this data set that match this data set, that match the first 8 rows of this data set. So what that means is we're going to get in the original data all of the information about the most common 8 words. Then we're going to drop a variable and we're going to do some other stuff. But so the goal of the pipe is to make it as easy as possible to express yourself in R, and then later on to hopefully be able to understand what it is exactly the heck that you were thinking at the time. Lots and lots of other examples of pipes. This is a little example using the Arvist package. Arvist is kind of like beautiful soup for R. It allows you to scrape HTML pages as easily as possible. So here we're going to start with the Lego movie, and we're going to select some nodes on that page. We're going to extract the text from those nodes, and then we're going to turn it into numbers. Or we're going to extract a slightly different set of nodes, turn that into text, that gives us the cast, another set. We accept the image, and we extract its source, and that's going to give us the URL for the poster of that movie. Lots of other examples. Here's an example from the purr package, which is designed to make R purr. It's also kind of a play on pure R, which I'll talk about what I mean by purity very shortly. So we're going to take the empty cast data set, we're going to split it into pieces based on the cylinder variable, we're going to fit a model to each piece. From each model we're going to extract a summary, and then from each summary we're going to extract the R squared. This is going to give us a numeric vector of length 3, 1 for each cylinder, giving us the R squared of that model. That's a pretty trivial example, but you can see hopefully how that idea of being able to rapidly work with lists of models can be really, really powerful. Another example is packaged by Scott, Analog C for working with DigitalOcean. So you get it, Analog C, DigitalOcean. Lets you create these droplets, little individual machines. You can create them, turn them off, turn them on, and you can read that very easily as a sequence of parallel operations. Another package by Scott that lets you work with gists. Another package by Stefan is for sort of like unit testing but for data flows. So you can use the insurer package to make sure at each step in your analysis that the data looks exactly as you'd expect. The goal in all of these packages is to make it easy for you to solve complex problems by combining simple pieces. So basically you're going to define some atoms, some building blocks, and then we're going to define the molecular bond of the pipe, and we're going to use that to create really, really complicated elements. So I think this is a great strategy for dealing with complexity. You have simple pieces that you can easily understand in isolation. You deal with complex problems by combining many of them together. So the goal is to get something like this, right? We have building blocks like Lego, and we can create something really complex and rich from them, even though the individual pieces are very, very simple. So I think there are 3 principles you want to follow if you're going to create an interface that uses pipes. The functions should be pure, which allows functions to be easily understood in isolation. So pure is a technical computer science term. I'll talk about what that means shortly. They should also be predictable. So once you've learned one of the building blocks, it should be easy for you to learn the other building blocks. And then finally, they should be pipeable, which is sort of predictable across packages. You should have a common way of combining these atoms together. You should have a common molecular bond, regardless of what package you're using. So the goal of purity is to make sure each function can be easily understood in isolation. And a function is pure if its output depends only on its inputs and it makes no changes to the state of the world. So I'm going to give you guys a quick challenge. I'm going to brainstorm for 1 minute what are some really common and important functions in R that are not pure. You have 1 minute starting now. Time's up. Anyone want to yell out one function that they think is not pure? Print. So what does print do? It doesn't change. It doesn't really do it. It doesn't give output. It just changes the state of the world by printing something on the console. What else? Plot. Same kind of thing, except instead of affecting the console, it affects the graphics device.
Rename.
So, rename. Rename from which package? I think generally, so rename, at least in all of the packages I've written, a rename function, which is unfortunately more than one, it tends to not do anything. It returns a modified object. So it doesn't affect the state of the world, and its output just depends on its input. So we have two examples here of print and plot that make no changes to the state of the world. What about a function whose output does not depend only on its inputs? And there are at least two of these that I guarantee you've probably used in the last week. Well, download.file, that's a really good one, right? So anything that depends on something external, like download.file, it doesn't just depend on the URL, it depends on what's at the URL. An even more common example is read.csv. Right, read.csv obviously doesn't depend on just the arguments, it also depends on what's in that file. There's another really, really common case, a function that has no arguments, but sometimes returns different things. That's a good one, list.files, what's in your current directory, something even kind of more basic than that. Sample is a good one, or RUnit, right? Any random number generator, a random number generator is going to be useless if its output only depends on its inputs, right? Because you'll get the same numbers every single time. So there are lots and lots of these functions. Sys.time is another one. Obviously, each time you call that, it's going to be different, even though it has the same arguments. Library, someone else mentioned. Library works by changing the state of the world. It adds the package to the search path. So now when you type the name of a function, R also looks in that package. Plot, options is another one, source is another one, the S4 class system, whenever you create a class or a new generic or a new method, effectively what you're doing is changing some hidden variable somewhere in the depths of R. So impure functions are really, really important, but they are more difficult to reason about because you can't understand them in isolation, right? You can't look at code that uses read.csv and know what the output is going to be. And in fact, if you combine that, say, with the global option strings as factors equals false, you don't even know what the column types is going to be. So depending on a global setting, sometimes read.csv will return factors, sometimes it will return character vectors. Right? That makes your life difficult because you can't predict what it's going to do without knowing much, much more about the enclosing environment, the general environment that's called for. So pure functions are really great because you can understand them in isolation. You can look at a pure function. It doesn't matter what else is going on in R. You always know what a pure function will do. You can read the source code and see exactly what it does. It has a couple of other benefits. It means that the pure functions are really easy to parallelize. And it means they're also easy to memorize or cache. Because the output of a pure function only depends on its inputs, if you have a function that's really complicated and takes a long time to run, you can run it with a set of inputs and save that output. If you ever see that set of inputs again, you can just return that saved output. Because the function is pure, you know you're going to get the same results. Now, there's lots and lots of useful things you can't do with purity. So some programming languages, so for example the Haskell programming languages, tries to push this idea really, really far. So pretty much every function in Haskell is pure. Now obviously a programming language that can't print anything out and can't take any input from the user is not going to be terribly useful. So Haskell has sort of various ways of getting around this that rely on more complicated mathematical ideas. But I think it's sort of a really interesting idea, like how far can you get if you only work with pure functions? Now that's sort of an interesting intellectual challenge, but practically, if you can isolate impurity to just a handful of functions, you're going to make your life much easier because you can more easily reason about those functions, you can more easily test them and so on. So if you do that, I think generally it leads to code that's easy to understand and easy to use for new purposes. And I'm going to show you one little case study of that. And how many of you used plot.lm before? Okay, so let's... So let's just do a little example of that. I'm going to create a model. Can you still hear me okay? I'm going to put a little model and I'm going to plot that model. And when I do that, I get this sequence of plots that show various different model diagnostics. Let's have a look at the code for plot.lm. Use the get S3 method to get this. Let's take a look at this code. We're just going to scroll all the way up to the top. Scrolling, 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 still scrolling. Here we go. So plot.lm is actually really, really complicated. And it's hard to understand exactly what it does. Because it intermingles things that are pure, so it does some data manipulation, it extracts some useful information out of the plot object, and on the other hand, it also turns that useful information into 4 or 5 different plots. We can contrast that with the fortify. So when I was working on ggplot, I found this really frustrating because plot.lm does all of this great stuff, but you cannot take advantage of it in any other plotting system because the data transformation and the plotting is so tightly intermingled. So in ggplot 2, I have a similar function called fortify.lm. It just fits on one slide. All this function does is extract the things that you want to plot from that model object. So you can see we compute some influence measures, we calculate some distances, some predictions and residuals. But you can understand exactly what this function is doing in just a few minutes of study. So now you can take that and you can take that data, you can visualize it any way you want, using any plotting system you want. I think that's a really important principle. So this is a pure function. Its output only depends on its input and it makes no changes to the state of the world. Now, if you'd like to see that idea explored in more detail, the Broom package by David Robinson is really fantastic. It does this for a very wide range of classes and models. Classes and models and turning models into tidy data frames that you can then manipulate and plot and even kind of model if you want to. So that's purity. So writing functions that this output only depends on the input and don't affect the state of the world in any way. The next component that's really important is that your function should be predictable. So once you've mastered one building block, you should have a good idea how to use all the others. So there's a few kind of easy things you can pick on R, and I'm just going to show a few of those to get some easy laughs. So what happens if you concatenate the numbers 1, 2, and 3 together? Hopefully you should have some strong mental model of what's going to happen. Oh, I get a vector of the numbers 1, 2, and 3. What happens if I concatenate the letters A, B, and C together? Oh, I get a vector of the letters A, B, and C. What happens if I concatenate, well, let's make this consistent, a factor A, a factor B, and a factor C together? What am I going to get? Everyone got a prediction in their head? We get the vector 1, 1, 1. So if you understand how factors are implemented behind the scenes, this kind of makes sense, but I can't see any practical use for this behavior in any possible scenario. Here's another little example. So let's do diag 4 to 1. So the diag function creates a diagonal matrix here with the numbers 4 to 1. What if we do diag 4 to 2? What do you think we're going to get? We get a diagonal matrix with the numbers 4, 3, 2. What if we do a diagonal matrix with 4 and 3? We get a diagonal matrix with the numbers 4 and 3. So what are we going to get if I do diag 4 to 4? Oh, I get a diagonal matrix of size 4 with 1s on the diagonal. Now this problem, diag's not that common. This also, you'll see this in sample. This is a little more insidious. So if you do sample 4 to 1, you'll randomly reorder those 4 numbers. If you sample 4 to 2, you'll randomly reorder those 3 numbers. If you do sample 4 to 3, you'll randomly reorder 4 and 3. If you sample 4 to 4, well, it samples the numbers 1 to 4. So this sort of behavior is something that makes R kind of frustrating to learn because you think you understood what happens and now you give it a slightly different input and the function doesn't work. Here's another one. How many characters in the string NA? Hopefully 2. How many strings in a missing character vector? Oh, that's also 2. That's strange. So it's kind of easy to pick on R for these things, and I think deservedly so to some extent. But unfortunately, it's basically sort of impossible to fix these problems. So you have to remember that every member of R core was at some point in their lives a beginning R programmer. And at the time they were working on R, they were the only R programmers, so they made mistakes. And everyone makes mistakes. I make mistakes all of the time. So you can't kind of hold these mistakes against R. And unfortunately, it's now very, very difficult to change them because the chances are that someone's code relies on this behavior. And if you change the code, you're going to break a whole lot of, if you change R itself, you're going to break a whole lot of code, which is obviously a bad thing. So that's kind of like some cheap laughs. But what I'm really interested in, I think is more important, is this type of inconsistency. So we have some string manipulation functions. I keep forgetting my laser pointer doesn't work here. String manipulation functions, don't even get me started on the names, like grepl, and I always think of like Greg's expression and str_split. But the thing that's frustrating here is the order of the arguments change, right? You've used grepl, you know the pattern comes first. You use that with gsub, oh, the pattern also comes first. You use Greg expro, pattern also comes first, and then you've got to use str_split, oh, and the pattern comes second. That just makes life a nightmare. Or if you have read.csv and write.csv, you have read.table and write.table. So what do you use if you want to read and write an RDS file? Oh, well, you use write, capital RDS, and you use save, capital RDS. Right, this makes, because of this sort of lack of symmetry, this lack of consistency and predictability, it makes your life as an R programmer much, much harder. Another thing that is difficult, I think, is that, to me, I think of there's 2 types of subsetting. There's preserving subsetting and simplifying subsetting. So preserving subsetting always gives you the same thing back. So if you use preserving subsetting with a matrix, you always get a matrix back. If you use it with a data frame, you always get a data frame back. If you use it with a list, you always get a list back. And then there's simplifying subsetting, which tries to give you the simplest possible thing. So you might get you use it with a list or a matrix or a data frame, and you might get a vector back. And unfortunately, there's a sort of inconsistency there depending on whether you're subsetting a list. If you use the single square brackets, that's preserving subsetting. If you use double square brackets, it's simplifying. But for matrices and data frames, we have this different drop equals false argument. And this is kind of a good example if you have a popular tweet I did recently. But if you ever have trouble remembering the difference between a single subsetting operator and a double subsetting operator, here is a little demonstration inspired by my stay at the Residence Inn, which had a rather interesting pepper shaker. So if you think of this as a list, and you subset it with the single square brackets, you just get this pepper shaker back containing a single packet of pepper. If you use the double brackets, you get the pepper inside that shaker. And then finally, if you subset that again, you actually get the pip. So why is predictability so important? Well, it means you can learn things once and then apply them in many different cases. You don't need to waste your precious cognitive resources memorizing all of the idiosyncrasies of different functions. You don't need to memorize all these special cases. That also makes it much, much easier to teach. You can just teach, this is the general principle. You don't have to teach like every individual special case. And in fact, like the string out package, the reason I wrote that is because when I was teaching my students regular expressions, I found it incredibly unappealing, the fact that you just have to say, well, if you want to detect if a string matches a pattern, well, you use grepl. I have no idea how you're going to memorize that grepl does that. You just have to memorize that. You have to memorize the order of the arguments. And so that's why I wrote the string out package, where all of the arguments are consistent, and the names, at least in my opinion, are a little easier to remember, like str, detect, and match, and replace, and so on. And the other kind of cool side effect of that, and something that Garrett at our studio has been taking advantage of, is if you can do that, often you can fit all of the main ideas on a single piece of paper. You can make a cheat sheet that allows people to get kind of the big picture of the package, to jog their memory of how everything works on just one piece of paper. Now, if you're going to think about punctuation, there's lots of, if you're going to think about consistency, there's lots of things you need to think about. You need to think about punctuation. If you're going to have multiple words in a function, how are you going to separate them? So there's snake case basically on one hand and camel case on the other. You need to pick one. I don't really care which one you pick. I think you should pick snake case, but I'm not going to hate you if you pick camel case. I will hate you, however, if you use both, particularly if you have a function that uses both underscores and capitalization to separate words. So the important thing with like consistency, it doesn't really matter what standard you pick, but you stick to it. When thinking about function names, you need to think about, am I going to use verbs mainly, or am I going to use nouns? You need to think about plural versus singular. Are you going to stick with UK English or US English? And my personal recommendation after writing ggplot2, which does understand both colour spelled correctly with a U and incorrectly without a U, I would strongly advise you to just simply avoid any word that is spelled differently in English and real English and American English. You also need to think about the names of arguments and the order in which they come. And I think it's also important to think about, like, what sort of objects are you going to work with? And I think it's useful to know a little bit about the S3 object system. So if a built-in object doesn't do exactly what you want, you can easily come up with your own objects tailored for the problem at hand. But again, it doesn't really matter what type of object you use as long as you're consistent about it. And some of the most frustrating functions are other functions that are not consistent. So for example, the sapply function, well, you never know what you're going to get. So I sometimes think it should be called like the box of chocolates function. So let's just say we have a vector, a numeric vector of length 5, or let's just start with a numeric vector of length 3, and I'm just not going to do anything particularly useful. I'm just going to get the length, say. So if I give it a numeric vector of length 3, I get a numeric vector of length 3 back. If I get a vector of length 2, I get a vector of length 2 back. If I use a vector of length 1, I get a vector of length 1 back. If I use a vector of length 0, which is admittedly a little esoteric, but it does happen, I get a list back. Right, this makes sapply extremely difficult to program with, because for some weird input, you're not going to get a vector back, you're going to get a list back, and your code is not probably going to give a nice error message. It's going to do something weird, and the user will get a completely incomprehensible error message, which of course R is famous for, but you should try and avoid doing that. And that's basically why you should never use sapply in a function. You should always use vapply, which is a little bit more specific. You give it let's do this again, a numeric of vector length 0, you compute the length. The other argument that you give to vapply is what you expect the function to return. So here I expect the length function to return an integer vector of length 1, and when I do that, now I get the correct result when I give a 0 length input. Now, that said, it's not possible to be kind of mutually consistent along every possible axis. So for example, if you look at read.csv and write.csv, well, read.csv as file is the first argument, and write.csv as file is the second argument. Right? That's inconsistent. But then if you look at all of the other functions that work with data frames, the data frame is always the first argument. And in fact, this is actually pretty nice, because if you create a chain, a pipeline of transformations, you can save the result here with write.csv. So it's impossible to kind of mutually satisfy every possible set of consistency, but I think it is really important to think about it and consciously make the trade-off between different forms of consistency, or consistency with different things. And that's something that's really difficult to do. So for example, dplyr and ggviz are not consistent because well, show you a little example of ggviz. So if you use ggviz, I'm not actually going to run this code, I'm just going to write it, and you can imagine that it works perfectly. But with ggviz, you're required to be explicit about using variables rather than using variables in the data frame rather than variables in the current environment. So you have to say, you have to put this tilde, this quoting character in front of variables that exist in your data frame rather than variables that exist in the current environment. Whereas if when you're working with this data in dplyr, you don't have to do that. Probably I'm not going to remember the exact, just imagine this is something useful that you'd want to do. But here, right, here you always have to put a tilde in front of the expression, here you don't. So even within my own packages, I'm not consistent. And that's because the other problem with being consistent is what happens if you make a mistake? If you make a mistake and publish it, now you've got a choice. Do you want your new work to be consistent with the mistake? So do you promulgate that mistake throughout everything else? That's bad, obviously. Or do you want to start with a clean slate and be inconsistent with your previous work? That's also bad. So you've got these sort of two bad options. This is one reason like my packages tend to not just evolve sort of within themselves, but to turn into other packages. So for example, there was reshape, then reshape 2, and then tidyr. And that's because sometimes you just have to break with the past. And it's better to make a clean break and kind of completely rethink how things work rather than trying to be partially consistent with your mistakes and partially consistent with what you think is now the right thing to do. I should actually let me give you one other little interesting historical anecdote. And the other type of inconsistency here is the inconsistency between ggplot2 and ggviz, right? Because in ggplot2, you write something like this. You use plus to combine things. So ggplot2 and ggviz are inconsistent. Now there's sort of an interesting historical anecdote, and that is if you ever use ggplot, which basically no one ever did, you would have written code like this. So one really interesting thing about ggplot is that if I discovered the pipe, like when I was writing ggplot2 never would have existed because it just would have rewritten function composition in a way that was easier for people to use. So I talked about purity, that's functions that can be easily understood in isolation because the outputs only depend on the inputs and they don't affect the state of the world. I've talked about predictability, so once you've understood one function, you can understand all of the functions of that set. And then finally, I want to talk about pipeable. And this is basically functions that are consistent across packages, that they use this common molecular bond of the pipe operator. So the pipe operator is nice because now when you use a new package, you can kind of assume that this is a standard way of combining pieces. Every time someone creates a new package, you don't need to rethink this from scratch. So I spent a lot of time, like it took me a long time to realize that, hey, using plus for ggplot2 made this code much, much easier. And then when I was when I started working on dplyr, I spent a lot of time thinking about like what should a grammar of data manipulation look like. In the same way that it's nice to have a grammar of graphics, it's also nice to have a grammar of data manipulation, which kind of allows you to separate out the idea, like I want to do this sort of manipulation from its concrete action on the specific data set. And I spent a lot of time like thinking about how can you do that, how should I do that with dplyr, and then realize that, hey, if you have this functional interface, you have this way of rewriting functions so they're easy to understand, you don't need to think about that anymore. So now if I want to create a package that gives a fluent interface, an interface that is easy for people to learn and use, I can do that very, very rapidly because I know the best way to do that is using the pipe and function composition. And basically, a package doesn't need to know anything about the pipe. It just needs to adopt the simple convention that basically you have one key object that's being transformed. That should always be the first argument, and it should always be returned by the function. So the key thing is here, you have to identify what that is. So like in dplyr, for example, that's data frames. In ggvis, it's visualizations. In analog C, it's this droplet object. You can transform from one type of object to another, and in a sense, like tidyr only works with data frames, but it works with a sequence of kind of the most messy data frame to the most tidy, changing over time. It is fine in the course of your pipe to change from one type to another, but you want to be explicit about it. And again, I can show a little example of that. Let me just modify this guy here. So, one nice thing is you can actually interleave ggvis and dplyr code because they use the same way of combining pieces together. You can easily interleave. That's not a very useful thing to do here, but you might want to do something more like this. You might want to do a filter. You want to say, I only want the cylinders less than 5, and you can just interleave that in your graphics pipeline, which is really, really useful because whenever you do graphics, it's typically you don't just have to update the visualization, you also have to modify the data to do what you want, to see what you want. So lots and lots of examples of this. dplyr works with data frame, ggvis with visualizations, gist with get.gist, per with vectors and lists, tidyr takes messy data and gradually makes it tidier and tidier, arvis works with HTML pages and nodes and lists of nodes, stringr works with strings, analog C works with droplets and actions. Right, so once you've identified that key object that's going to be modified, you've wrapped that up in an S3 class, then you can easily make these little building blocks that are easily understood in isolation. You solve complex problems by joining many simple pieces together. I wanted to finish off by talking a little bit about the Magritte package, some of the extensions that it provides, some of which I really like and some of which I'm not so in love with, and some of the limitations. So the goal, hopefully, you realize, is not to take every data analysis you've ever written and turn it into a single pipeline. That's just ridiculous. There's definitely places where this works well. I think it works well, for example, when you have a linear sequence of events, a linear sequence of transformations. It can make sense if you have like one main object and each point you're adding in some kind of sub-object. This is really common if you're joining on additional lookup tables. You have a main table, you want to add additional metadata. And you can even do that sort of in moderation with sub-pipes. Although once you start getting more complicated, I think if you try and do that everything in one pipe, your code starts to get really complicated. There are also situations where I think this is a really bad idea, like this sort of case where you don't have a primary object at each point. And if you know anything about like graphs or trees, you might have noticed that, hey, this, which I say no, is exactly the same as this, where I say yes, but I've just moved the nodes around a little bit. And that's because I think conceptually there is a big difference. Here there is one primary object, here there is not. With pipes you can only have one output. I mean, there are ways to have multiple outputs, but I think they're generally kind of clumsy, and you can't have loops. So I think, you can kind of fight with R to make any of these things possible. R is an incredibly flexible language. Pretty much anything you can imagine you can do. And I really like to think of it as like, R gives you a loaded gun and lets you point it at your foot and lets you pull the trigger, but you have to exercise that self-restraint yourself. A lot of other programming languages, they don't give you a gun, they give you like safety scissors, which, you can't cut yourself on them, but it's really difficult to do anything with them as well. Right? There's always this trade-off between kind of safety and power. So I said you can't do loops. Well, actually that's not quite true, because Magritte provides this kind of double-ended arrow, which lets you replace the thing on the left-hand side after it's been transformed by the thing on the right-hand side. So it's a shorthand for this common pattern, where you take an object, because when you call mutate and it adds a new column, actually it doesn't add a new column, it creates a new data frame with a new column. But sometimes you do just want to think about it as I want to add a column to this data frame, even though that's not a great mental model. But sometimes you do just want to do that, and you can do that with this operator. Now, I don't love this operator because I think assignment is so important and so key that you should never hide assignment. You should always make it absolutely clear. Like this is impurity, right? Assignment, we didn't mention this before, but the assignment arrow is fundamentally impure, right? That's really, really important not to kind of hide it in the midst of purity. Now, there is one really cool thing I like about Magritte that not many people know about. So often you'll find yourself doing the same sets of transformation on different inputs. What you can do in Magritte is create not just a specific pipeline that transforms a data set, but a generic pipeline, a function that can transform any data set. So if the first thing you put into a pipe in Magritte is the dot, you get a function back rather than a concrete set of transformations. So in other words, if you run this code, the first thing in my pipe is the dot. ToMetric is going to be a function. And I can give any data set to that function, and it will run that sequence of transformations through it. So this is shorthand for creating this little function that does the transformation. I think that's pretty cool and pretty useful. And it's a little bit magical, but once you've seen it once, I think you can kind of figure out, hey, when I put a dot as the first argument, I'm not creating a specific pipeline anymore, I'm creating a generic pipeline that can transform anything new that I give it. So in summary, if you want to make your own fluent interfaces, your own interfaces that allow people to express themselves naturally by composing small pieces that are easily understood, you should create these pure functions whose output only depends on the input and don't change the state of the world. Those are easy to understand in isolation. You should make sure they are all predictable, they should be consistent, so once someone has learned one, they can learn all the others. And finally, you should make these more complicated things. You should solve more complicated problems by joining these simple pieces together with the pipe. Thank you. We have time for a few questions, I think. Jared, you'll tell me when we have to pick people out.
An hour.
I'm not going to take an hour of questions, but I'll take a few. Yep.
So, this is something I've been wondering. Philosophically, how does the pipe relate to the methodification of the dot in JavaScript or Python?
So the question was, to paraphrase, basically in other programming languages, in traditional object-oriented programming languages like JavaScript or Python, you'd write this as something like that. You'd write it as a sequence of method invocations, which is a common style called method chaining. So I think method chaining is very similar to the pipe. The big difference between method chaining and the pipe is that only the creator of this object can add new functions to it. Only the owner of this class can add new methods that you can chain. With the pipe, anyone can add methods. So I think there's like, the pipe, you have to be a little bit more explicit about where these functions come from, but the cost is anyone can create a sequence of pipes across, they use functions from multiple packages, even if the original authors never intended that.
The trend these days is mixins, which is you being able to add new methods to an existing class.
So you call them mixins. I think the other common name is monkey patching.
Yes.
Which obviously has a slightly different connotation than mixins, yes. But yeah, I mean, there's many different ways of solving the same basic problem across programming languages if you use a traditional method-based, well, if you use method passing-based object-oriented, that's more natural. R uses generic functions, so this pipe idea is more natural.
So to achieve predictability with code, are there any set of kind of like published guidelines you think we should put as a bytecode?
So the question was, are there any published guidelines to that you should sort of hold as the word from God about what you should do? I mean, I certainly have opinions about things. Like in terms of code style, at least, I have guidelines. Style guide. No style guide is really better than any other style guide. The whole point is being consistent. But obviously my style guide is the best of all possible style guides. So I think basically what so there are no written guidelines. You have to kind of decide what you want to be consistent with. And if someone, there's also this, if I can, this XKCD on, I think like standards maybe. Yeah. Right, there's this problem that, R is not consistent now. There probably are like 14 different competing ways to do things in R. So if your goal is to say, that 14 is ridiculous, we're going to create one standard to rule them all, actually what you've done now is there are now 15 competing standards. So I think Bill Venables had a nice talk at UseR a couple of years ago about sort of R empires, which are like sets of packages that seem to work naturally together. I think you kind of need to think about like which empire do you want to belong to, and you need to like copy the rules of that empire. So the question was, and I'm just going to paraphrase your question to make it a question that I would rather answer. It's basically like, what about typing? So many programming languages have this idea that you should pre-specify the types of all of the inputs to a function, the type of the output of that function. And I think like typing in that sense is helpful, it's helpful in the same way that purity is. That like 80% of the time, it's great to be pure. 80% of the time, you want to be specific about the types of things. And then the other 20% of the time, you want to kind of break free from those constraints. I think there's some nice work that's been done to add sort of like type hinting, which is anything, you can do anything. Like you can write, maybe I can write this function one-handed. You can write a function like this. Okay, I'm going to put this down because that's too frustrating to type that slowly. You can write a function like this, right? If x is less than 0, return 1, otherwise return a. Right? So this function sometimes returns a numeric vector, sometimes it returns a character vector. Now in this case, that's obviously a really bad idea, but there are some cases where that's important. For example, like read.csv, you don't know in advance when you have a CSV what the types of the columns are going to be. There's some interesting work going on in F#, and it's, I forgot the name of it, but there's some way of sort of dynamically adding these types. I think it would be interesting for someone to explore that in R. Some of these things could be picked up automatically, some of them you just have to stick to conventions. So the question was like, how does piping relate to traditional functions in terms of memory usage and other things like parallelization? And basically, it has there's like a tiny amount of overhead with the pipe. But really, what happens when you run this code, it gets converted to something that looks very similar to that. So what this operator does is converts your code to this, and then R just executes it the ordinary way. So there's basically no implications to how the code runs. Exactly. So I'm sort of lighting a few details. There's a little bit of overhead to that, but to the pipe. But basically, just think of this as this is a transformation for humans. It makes your code easier to read. It doesn't fundamentally change how it works. Thomas?
What do you think about if you're using a pipe, using the right arrow instead of the left arrow, so that your assignment is at the end of the pipe rather than the beginning?
Yeah, so again, maybe some of you know, or if you don't know, you can do this in R. I certainly don't want you to learn that you can do this. You can actually do assignment in either direction in R, which I think is pretty crazy. Now, it sort of turns out that maybe if you do, a sequence of transformations, some other ... At the end of that pipe, you can assign to something. Now again, I'm basically divided on this, because in some ways I think, wow, this is really cool and elegant and nice. On the other hand, assignment is so important that, again, I think it's just such a bad idea to break with the conventions. It's also nice. The other thing that's nice about the name of a variable is if you've picked this name of the variable well, it's going to give you a hint about what this pipeline is going to do. So I think writing it's a little more awkward, but reading it's kind of nice because you get this hint about what am I going to get from this pipeline. And hopefully, if you call it my result, that's useless. But if you call it something more descriptive, that's going to give you a hint when you read it. What's the goal of this sequence of transformations?
What's your take on the current state of object-oriented?
So the question was, what do I think about the different object-oriented programming systems in R? And there are now, I think, let's say 4 reasonably popular ones: S3, S4, reference classes, and R6. I think S3 for most problems is the right solution. I think if you want to understand more about why R looks so different to JavaScript, for example, or Python in terms of object-oriented system, you have to go back in time a little bit. And there really are, there's this fundamental difference in object-oriented systems. When you have a method, does it belong to the class or does it belong to the function? And in Python and JavaScript and Ruby and C#, the method belongs to the class. In R and in Common Lisp and in Dylan, the method belongs to the function. And I think that's actually I think that's actually the right type of object-oriented programming for the type of thing you do in data analysis. And interesting, this is the same type of object-oriented programming that Julia uses. It uses generic function style object-oriented programming as well. So I think that's actually, that's the right choice. So in most cases you should be using S3. S4, I think unfortunately to some extent what happened is that S4 suffered from this thing called a second system effect. Where basically the second system, let's make it a little bigger, the second thing you design is the most dangerous thing, because you're like, there are all these awesome things I should have put on that first system, and now I can add them all in. And then when you do that, you create this really complicated system, which I think S4 is a little bit overcomplicated for the type of problems most people need to solve in R. That said, it's nice, it's rigorous, it generalizes to many more situations in S3, but for most cases it's just too complicated. Reference classes and R6 basically do the same thing. Reference classes are kind of environments plus S4, R6 are environments plus S3. R6, I think, fixes one problem with reference classes and are much faster. If you do need that kind of message passing style object-orientedness, use R6. Why do I like underscores instead of camel case? I think basically at a time in my life I did a lot of Ruby programming, and basically Ruby uses underscores, and I somehow that's stuck. There's no real difference between them. I would really thoroughly be skeptical about any study that showed that like camel case was better than snake case or vice versa. I really don't believe it has any cognitive impact. It's just a matter of convention. Unfortunately, there's no, like, our language not adopt one convention, like even RStudio, unfortunately, like if you look at Shiny, Shiny uses, even within RStudio, we're inconsistent. Some packages use camel case, some packages use snake case. And, if you go back in time and enforce that, that would be awesome for everyone, but you can't. So we're in this state forever. So the question was like, what's the future of Shiny? And I really, whenever anyone asks that question, I cannot resist saying the future of Shiny looks very bright. I kind of really want Joe to release Shiny 2 and call it Shiny 2 the polishing. But I think so Shiny is, I think, a really powerful tool for creating, telling other people what you've done. I think the main challenges for Shiny are teaching people how to use it effectively. I've had a number of cases where people come up to me at a conference and say, there's something wrong with my Shiny app and I can't figure it out, and they show me this thing and I have to freeze my facial expression to not show the sheer horror I'm experiencing. I think so. People are creating these 5,000 line Shiny apps, and then they don't work and they don't know how to fix it. And that's not their fault. That's our fault. We need to do a better job of teaching people how to write Shiny apps that you can actually understand and debug. I think the other big thing that needs to be improved is better debugging tools for Shiny, and then finally also better profiling tools. If your Shiny app is slow, it's really, really difficult to understand what's making it slow. And this is hard, but it's hard enough to understand what makes your R program slow, but now you have all these changing inputs and outputs and trying to figure out what is making the whole app slow is really hard. So I think better, how can we help people write better Shiny apps? How can we help them better debug their apps and better profile their apps? I think those are the big things. I think there will continue to be more, nice HTML widgets which let you use the power of existing JavaScript libraries. I think performance of Shiny itself will continue to improve, but I think of Shiny, the big picture is mostly there. Now is just helping people understand how to use all of that effectively.
When piping, do you have any advices for I/O operations? Loading data inside, should we go inside the pipe? Should we create a function around it? Do you have any advice on I/O operations?
My advice for I/O operations, I think it's nothing really to do with pipes. I think you either should be using the readr package or you should be using ifread from data table, because they're way better. So readr, for example, and ifread is a little, I think, is a little faster, slightly less flexible, but both of them, in both cases, read_CSV and ifread are 10 times faster than the base read.csv function. And more importantly, I think the most important thing about these functions is they fail to do things, really annoying things that read.csv does. So for example, they never convert strings into factors. And they never munge your column headings and stuff like that. So I think otherwise, I don't know, your pipe normally starts with data input and it normally ends with data output, because that's, you have to load data from somewhere and you have to report it somewhere. So I don't really have any other advice.
What's your take on the error handling on the pipe? I often find the pipe just make my code so readable, so I write very, very long pipelines. And eventually something breaks in the middle that I cannot say set a breakpoint, and then I can do it.
Yeah, so the question is, how do you basically debugging pipes, particularly when you have long pipes? So my first piece of advice would be, don't do that. Don't write really long pipes. That said, I think there is It's something that Stefan and I have been thinking about a little bit. I think that there might be some better tools. There's currently some discussion happening in there's a pull request where Gabor has proposed this tamper function, which basically kind of lets you, when there's an error, it says, oh, this is the place where the error occurred, and then you can jump to it and debug it. The way that works is kind of complicated, but I think that's obviously going to be pretty useful for debugging pipes, so look for that soon.
Do you think there's any spaces for like promises where you can specify like how like on success you can propagate to the next level of failure, you can propagate the failure all the way to the end, like browse and many other levels?
I think that idea, like JavaScript, I think it's the sort of future objects which let you express sort of make it a little easier to express in generality what happens when something goes wrong with your pipe. I think that it might be useful to translate those ideas into R's error handling system, although without thinking about it deeply, it wouldn't sort of not clear to me how you do that in a way that feels natural in R.
Kind of going back, do you think is R ever going to become a boring mainstream language?
Is R ever going to become a boring mainstream language? I think to some extent it already has, right? Like Microsoft supports R now, like how more boring can you get than that? It's regularly, you only ever sort of believe like the IE programming language rankings. I think the IEEE ranked R as like it's kind of like 6th most popular programming language. And the way you interpret programming language rankings is basically whenever they agree with what you want, you're like, this is an awesome ranking, this captures exactly what I think. Yes, R really is the 6th most popular programming language. And then if they don't, you're like, well, there's all these problems with their methodology, there's no way that R is really that popular. And I don't honestly believe that R is the 6th most popular programming language. It's not more popular than PHP or JavaScript, that's just ridiculous. But the fact that it's even like in the top 10 or the top 20 programming languages is showing that R really is reaching this level of maturity. I think there's sort of other interesting stuff that's happening in the R community, like the R consortium. Like Google, we'll see if Google picks this up, but no Google, search for R consortium. Well, there is there we go, put a space in there. I don't know how many of you have heard of the R Consortium? So the R Consortium is basically a group of big companies like Microsoft and smaller companies like RStudio and TIBCO and Alteryx and Google and HP and Kitchen Trading and Mango Solutions and Oracle that have basically said like, hey, we really believe in R and we believe in it enough that we're going to put some money behind it, put some money into it so that the R Consortium has some like stable long-term funding to tackle projects that affect the R community as a whole. And I think that's a really good sign of R's growing up. And R growing up is good and bad, but I think by and large for R it's good.
I was wondering, I've seen your what are there any examples of
So the R Consortium has really only just started working, so it has not funded anything yet. I think I can't really talk about things that might fund yet, but there will, at some point in the near future, there will be like a process by which the consortium solicits ideas for projects that should be funded, and a process for like reviewing those and then actually funding them, and hopefully there should be some funded projects by the end of the year. Yep.
Do you see any plans to support objects more through memory reference rather than by value? Something like you mentioned data types there.
So there's a lot of confusion about how R objects are passed to functions, and for R this distinction between passing by reference and passing by value isn't actually a very good one, because the better way to think about objects in R is that objects are copied when they're modified. So whenever you think you're modifying an object in place, often you're actually creating a modified copy. Now R has some heuristics to figure out, so when you do you do x is 1 to 10, and you say I want to change the fifth element of x to 7, that's not actually going to create a copy. You can tell it easily enough, but nothing else refers to it, so it can modify it in place. Otherwise, I mean, R has got a lot better in the last few versions now when it copies things. Previously, if you had things on a list and you modified that list, R would do a deep copy. Now it just does a very shallow copy, which makes things much, much faster. I honestly don't think it's a huge problem. There are moves afoot internally in R to make these heuristics better so it does modify things actually in place more often rather than creating a modified copy. But I personally don't believe R needs any more things for handling references that it already does. Let's take one last question. Anyone have like a burning question they simply must have answered?
Recursion and piping or just like a function? Like
Yeah, again, recursion and piping is just like a function.
just use it like assignment.
Yep. Any more? That was an easy question. Okay.
What are your thoughts on storing more complicated variables in data frames? Let's say fit objects versus analysis.
So the question is, what do I think about storing more complicated objects in data frames? I think it is an awesome idea. I think it really makes sense. It's a little mind-blowing at first, but for example, having a column of a data frame that's a list of linear models is an awesome idea, and my packages like tidyr and dplyr and so on will be doing more and more to support that over time. It's a great idea. It's a great technique. Okay, thank you all for coming, and I'll be joining you for drinks afterwards.
So first off, thank you to Hadley for an amazing talk. Second, we found the bar, but before that, I forgot to do the giveaways. Do you guys want free stuff?
I do.